Hi everyone, this video is going to serve as a gentle introduction to the laborious technical details of the SABR model. In its most popular form, it assumes that the price follows a constant elasticity of variance model. This is the SABR model, where alpha, which represents the volatility, is assumed to be stochastic. It follows geometric Brownian with zero drift, and nu is the volatility of volatility. The SABR model popularity is not due to these dynamics, but rather the approach used for deriving an approximate formula for the prices of European option, which then allows for adjusting the Black's volatility so that it produces prices that are consistent with the smile observed in the market. One can equally apply the same procedure to, say, the Heston stochastic volatility model. What we are trying to say is that the particular dynamics are not as important as the underlying solution methodology. So in this video, let's apply the thinking to the simple CEV case in which the volatility is not stochastic. We will assume alpha is constant, but the derivation should work if you assume that alpha is a deterministic function, say of time. It is essentially a parametric local volatility model, right? Now, as you would know, one can derive a formula for the price of a European call option under these dynamics, but it involves non-central chi-square and requires a lot of calculation, so some sort of approximation is usually implied. Hagan et al. Adopted a different approach to derive an approximation formula. It uses perturbation methods, which were introduced to tackle the orbits of planets. For example, in the ideal world, Earth would revolve around the Sun in a nice ellipse, but the presence of Moon and other planets make it wiggle slightly. The perturbation methods were introduced to capture this deviation from the ellipse. These methods have since evolved and are now widely used in a wide variety of contexts, but in the context of the present problem, you can view it as an approximate method for solving a PDE, just like numerical methods are used to solve PDEs. Say you have derived the exact solution of the diffusion equation, but have now been asked to determine the solution of a slightly modified version of the diffusion equation in which the coefficient is no longer a constant. You can introduce a small parameter, this is the epsilon, and now if epsilon were to be 0, this would reduce to the simple case of constant coefficient. And as epsilon goes to 1, the equation will approach the problem we are supposed to solve. If the behavior of the solution doesn't change dramatically at 0, then it is called a regular perturbation problem. And if it does, then it's called singular perturbation problem. This is just some terminology you will see in the derivation. One then just tries a sort of power series expansion to approximate the solution. This power series looks a lot like the simple power series, but is fundamentally different in terms of convergence properties and truncation error. But this doesn't matter for our purposes here. As they say, the proof of the pudding is in the eating. So you can judge the quality of the approximate solution to see how good it is. And that's the approach we are going to take here. By the way, the process for applying the perturbation methods is usually mechanical but laborious, as we shall see. So we delegate some of the sub-derivation to sub-videos so that we don't lose sight of the big picture. Now, the derivation in this video is pretty similar to this heat equation problem, though the coefficient is more complicated and one has to transform the equation to get it in the right format, and one then has to apply a lot of interpretation to express the result in a useful form. The procedure we are going to adopt is not the only way to approach the problem, but this is what Hagan et al. Use, so we follow these steps, and you should view this as the first generation model in this space. Some of the decisions might appear arbitrary, and they are very much so, as more robust approaches have been found since then, but we shall see by the end of the video. One can only marvel at the stamina, patience, and ingenuity of these guys, and then, like I said earlier, the proof of the pudding is then in the eating. So let's get started. Now this equation is not much different from the Black Scholes. Remember, the stock price there follows a geometric Brownian process. We don't have the drift term, and this is why it's called the Black model as opposed to Black Scholes. And in place of S, we have F, which is like the forward price. Alpha does the same thing as sigma. The most significant change is that we have F to the power beta and the diffusion term in place of S. If beta equals 1, then we have the same log normal model as Black Scholes with zero drift. And if it equals 0, then we have the normal model. The beta is supposed to be between 0 and 1. The reason for introducing the analogy with Black Scholes is we can easily deduce the valuation PDE. Let's say we are pricing a call option, which is a function of time and the then current forward price. And as usual, we will write it as V without the arguments to make it readable. And then we know this price is equal to the discounted expected value of the terminal payoff. We know the Black Scholes equation is as follows. We have derived it before. Let's remove the interest rate to simplify the presentation. It won't result in any fundamental change, but will just reduce what we have to write. And let's represent the undiscounted expected value, which is like the forward price of the option, by Q. Of course, Q is a function of the two variables, but we don't write the arguments. We can now deduce the valuation equation for our dynamics. We don't have R, so the last two terms disappear. And we have Q in place of V, alpha in place of sigma, and F to the power 2 times beta in place of S squared. And because we are pricing a call option, the terminal condition is maximum of F minus K and 0. The plus sign is a way to indicate that the option pays F minus K if this amount is positive and pays nothing otherwise. By the way, you can also derive this valuation equation using Kolmogorov equation, but don't worry about this alternative approach for now, as we will encounter this approach in the future videos. As many of you would have anticipated, next step is to transform this problem. Just like what we did in the Black Scholes video, we transform it into an initial value problem, so that in place of terminal condition, we have initial condition, which means we define a new variable tau as remaining maturity. But here, this variable plays a much more important role. Remember, variance and time play similar roles in the diffusion, so we combine both of them and represent this by tau. So tau is, in a sense, the total variance over the life of the option. And this is the most important quantity of interest in the SABR model, as we shall see shortly. The next set of transformation is to cast the problem in a form to facilitate the application of the perturbation methods. One defines a new variable epsilon as k to the power beta. This is assumed to be small. Think of k as the strike price of an interest rate derivative and beta as ranging between 0 and 1. Next, we transform the spatial variable f to x. So it is like distance between f and k. In a way, a measure of moneyness. Remember, the moneyness is a key quantity of interest in the volatility smile. So you can see we are heading in the right direction. And then we can scale the option price by epsilon as well. Like I said before, these transformations are not the only way to the use of the perturbation methods, but we are following Hagan et al. So the motivation came from their paper. And like I said, we are viewing this as a first generation model. Nevertheless, though, these transformations do provide insights into what is at play here. Let's use these to transform our problem. Let's start with the terminal condition. But first, let's rearrange the last two transformations so that we have the whole variables on one side. We can then just substitute these expressions. So in the penultimate equation, we isolate f on one side, and then in the last equation, we isolate q on one side. Now we can replace f in the terminal condition. We just substituted this expression, and then the k's cancel. And on the left hand side, we substitute for q. Remember, when time equals capital T, tau, which is the new variable, equals 0. So q underscore capital T becomes epsilon times tilde q naught. And then the epsilons cancel. So the terminal condition has become an initial condition. And don't forget the plus sign and the power means we get x if it's positive and 0 otherwise. So it's essentially maximum of x and 0. Let's transform the PDE now. The time derivative will get transformed into derivative with respect to tau. So we just use the chain rule. And we then just need derivative of tau with respect to t, which is just minus alpha squared because capital T is constant. So we substitute minus alpha squared and then just rearrange the terms. Derivative with respect to f will get transformed into derivative with respect to x. So we again use chain rule. And then dx by df is just equal to 1 divided by epsilon because k is constant. The epsilons cancel. We now differentiate again because we actually need the second derivative. We use the chain rule again and then again substitute 1 divided by epsilon for dx by df. And we now have both of the derivatives. Let's replace the time derivative and then the spatial derivative. Let's isolate each derivative on one side. The alphas cancel and we can shift epsilon to the right hand side so it becomes squared. And now one last step will transform the problem into the desired form. We just substitute it for f and epsilon. And now we can expand the numerator around k in order to simplify the coefficient. We will be applying Taylor series, so best to represent it as a function f. We will take care of the square afterwards. Now in terms of the function f, we have f of k plus epsilon times x in the numerator. And think of this epsilon times x as a small value. And now recall Taylor series expansion up to the second order. We keep the denominator as it is and substitute the Taylor series expansion in the numerator. We then distribute the terms in the denominator to the 3 terms in the numerator. Let's abbreviate the terms. So we will represent the ratio of the first derivative to the function value by v1 and the ratio of the second derivative and the function by v2. And then the first term equals 1. So let's make the replacements. Now this is a plus b plus c squared. We know it equals a squared plus b squared plus c squared plus 2 times the 3 sets of cross terms. We retain terms up to epsilon squared, so this 4th order term drops, and so does this 3rd order term. We can simplify the individual terms and then rearrange. We can combine the x squared terms by factoring out epsilon squared and x squared. And we can now replace the square of the 3 terms by this truncated version. So the complicated nonlinear coefficient has become a linear combination of relatively simple terms. We now try an asymptotic solution. As we said earlier, it looks like a power series solution, but is fundamentally different in nature. Before plugging the solution into the PDE, let's change the derivative notation to create space. So q underscore tau represents the derivative with respect to tau, and q underscore xs represents the second derivative with respect to x. We can now take the derivative of our asymptotic solution with respect to tau. It's easy peasy as derivative of sum is equal to sum of derivatives. And let's make the replacement. The coefficient remains unchanged, and we then take second derivative with respect to x, which again is down to derivative of sum. And we can substitute this into the PDE as well. We need to get rid of the brackets, so let's take the first term in the first set of brackets and multiply all the terms in the second set of brackets by this term. We then do the same for the second term and then the third term. Now this is the kind of situation where one just equate the coefficient of different power and the main variable is epsilon. So we equate the terms containing no epsilon. These are the terms highlighted in yellow. They must equal if the equality were to hold for all values of epsilon. Next, we find the coefficients of epsilon. We highlight them in green and equate the coefficients on both sides of the equality. And we then do the same for the coefficients of epsilon squared. Now we have 3 equations to solve instead of 1, but they are easier to solve, so consider it a win. We need the initial conditions for all of them though. Remember, for the transform problem, we had determined the initial condition to be x plus, which is maximum of x and 0. So the left hand side has this as the initial condition. On the right hand side, if the asymptotic solution were to satisfy this initial condition for all values of epsilon, then it's easy to see that the Q0 must have this same initial condition. But the Q1 and Q2 will have 0 as the initial conditions. So let's write the initial conditions against the individual equations. And now we just need to solve these 3 diffusion equations, and then their combination will give us a formula for the price of a European call option. We have already seen similar equations before. The first one is just the homogeneous diffusion equation, which we have solved in the fundamental solution of diffusion equation video. Remember, there we started with the diffusion equation, subject to the initial condition, and then using the similarity method, we showed that this solution is as follows. In the present case, the initial condition is in terms of the maximum function, so the z is just equal to maximum of z and 0. And if we substitute this for psi of z, then we have the solution of our first equation. It looks formidable, no one likes integral, but as we showed in a sub-video, this actually simplifies a lot. This was covered in a voiceless video that some of you liked, but some of you found it weird. Anyways, have a go at the simplification, and if you need any hints, then let us know, and we will send you a link to that soulless video. And you can see this result is actually the price of a European call option under the normal model that we covered recently in another video in the same voiceless series. And the fact that we get the price under normal model plays an important simplification role when we want to bring the solutions of the 3 equations together. By the way, we will try to redo these sub-videos in the standard format at some point, so apologies for the inconvenience in the meantime. Let's move to the second equation. It is a diffusion equation again, but non-homogeneous. But we know how to solve this one as well. We have covered this in a separate video. But firstly, the source term contains the second derivative of the solution of Q0 that we just determined. If you take the second derivative of the solution, you will see it simplifies to just the normal density. So let's make the replacement. And now this is the non-homogeneous diffusion equation with initial condition equal to 0, and this is the source term. We know from the sub-video that the solution of this equation is this double integral. No one likes integral, let alone double integrals, but luckily we know from the same video that this integral simplifies to a scale normal density. So let's move to the third and final equation. The source term again contains the second derivative of the first solution, which as we saw before is just the normal density. This is multiplied by coefficients in the PDE, so let's multiply both sides by the same coefficient. The source also contains the second derivative of the second solution, which you can determine easily. It really simplifies to the scale normal density. Again, this is multiplied by coefficient, so let's multiply both sides by the same coefficient. We can get rid of the brackets by taking v1 squared times x inside, and we can make the replacement. Now we can substitute these into the PDE. Both terms contain the normal density, so we factor out the normal density and then write what remains of the 2 terms inside the brackets. And we can now use the solution of the non-homogeneous equation. It's the same double integral, just the source term is slightly longer. But nevertheless, as is often the case with integral involving normals, it simplifies a lot. So we have the solution now. It gives us the price of the call option, or a transform of the price, because remember we transformed the variables. It's not hard to calculate, but more magic is possible. The main idea comes from the fact that the tilde Q naught represents the price of a European call option under the normal model. The other two terms can then be written as the derivatives of the normal price with respect to tau. Let's see. If you differentiate this with respect to tau, you will get half of the normal density. And if you differentiate again, you will still get the scaled normal density, though the scaling factor is slightly complicated. Now, if you look at the expression for Q1, you see it has half the normal density, which is the first derivative of Q0 with respect to tau, and we keep the residual terms. So we get rid of Q1 by replacing it with the first derivative of Q0. Q2 is a bit longer, so we expect that we will be needing both the derivatives. Let's try to write the first term as the second derivative. So we add and subtract a term that will help us achieve that. Notice the normal density is already there outside the brackets, so we just need to get the scaling factor that we see in the second derivative. Let's factor out half of v1 times x squared. So we're just missing tau squared in the denominator. So let's multiply and divide by tau squared. So that's the first term sorted. Let's move to the second term, which we can rearrange. We can then combine the term we added to this term, and this the second term sorted as well. And let's add the third term. We need to do a bit of housekeeping now. Let's combine the fractions and the coefficients of x1 squared times tau term. So we write the common denominator 24 and then multiply the terms in the numerator to make this denominator work for all of them. We can now combine the v1 squared terms. Essentially, we are just left with the v1 squared. Let's make the replacement. In the third term, we do the same, which is to combine the fractions and then make the replacement. Next, we factor out 1 divided by 2 and tau in the last two terms. This 1 divided by 2 is needed so that we can replace it by the first derivative. The first term now, when multiplied by the normal density outside the brackets, is a scale version of the second derivative of tilde Q naught, and the second term is just a scale version of the first derivative of tilde Q naught. We can substitute this expression for tilde Q2. And now is the time to see the result of our hard work. The hard work being playing with the derivatives of the normal model. The first term stays as it is. The second and last term contain tau and the first derivative of tilde Q naught with respect to tau, so we can combine them. We essentially factor out the first derivative and tau. The second term contains the second derivative with respect to tau and tau squared. It looks like a Taylor series expansion. So let's define a new variable, tilde tau. Then the coefficient of the first derivative is just missing tau times this one. So it is tilde tau minus tau. And this looks very much like the Taylor series expansion of the normal price with parameter tilde tau and expanded around tau. So the price of the European call option under the CEV model is like the price under the normal model, but evaluated at the transform value of tau. Magic in it. Remember, Q naught is given by this formula. We need to undo the transformations now to get the answer in terms of the original variables before we see another magic. The price of a European call option is the discounted expected value of the payoff. We represented the expected value of the payoff by Q, and we then defined tilde Q as scale version of Q. So our Q is equal to epsilon times tilde Q. Q tilde is a function of tilde tau and x. We would like to take epsilon inside the function q, which is easy. If you multiply the first parameter by epsilon squared and the second by epsilon, then the form of the solution will remain unchanged. We will just have epsilon times x in place of x, and epsilon times square root of tau in place of square root of tau. And this is nothing but epsilon times tilde q naught. So we can replace epsilon times tilde q naught by tilde q naught, evaluated at epsilon squared times tau and epsilon times x. Now let's undo the remaining transformations. Remember, we applied this set of transformations. So we replace epsilon by k to the power beta. This is as per the second transformation. And epsilon times x by f minus k. This is as per the third transformation. And let's represent this transformation of tilde tau by tau asterisk. And in this tau asterisk, we also need to replace epsilon and epsilon times x. Now this tau asterisk is like transform total variance, but in the Black Scholes, remember, we commonly refer to volatility instead, so let's take its square root. Remember the formula for the square root in terms of binomial expansion? Here we have a longer expression for x, but that's not a big problem. We can write the square root of the term in the brackets as 1 plus half times whatever expression we have in place of x, minus 1 divided by 8 times the square of this expression. This square will be a longer expression, but we don't write the higher order terms. We stop at the square, so the square contribute only one term. We have the main result now. We just need to link it to the Black Scholes. But before doing so, let's try to simplify and improve the approximation a bit more. Remember earlier we defined a function f of k as k to the power beta, and v1 is the first derivative of f divided by f, and v2 is the second derivative of f divided by f. To see the potential for improvements, let's focus on the first two terms inside the brackets times k to the power beta, which is outside the bracket. In terms of the function f, it can be written as follows. This looks like a Taylor series expansion of f of average of f and k. Let's see. These arguments will evaluate to average of f and k, as you can easily check. And we can write its Taylor series. It indeed resembles the previous equation, and we know the next term of this series will look as follows. So it is 1 divided by 2 times the second derivative times the displacement squared. So we can think of our extracted term as the Taylor series expansion of the function value, evaluated at the average of f and k. And like I said, you can easily check that this argument evaluates to average of f and k. And we represent this average of f and k by f underscore av. And you know the function f just means raise the argument to the power beta. We are missing the second order term in our equation, so we add and subtract this term. It is the same expression in terms of v2. Don't forget we have k to the power beta outside the brackets. So the sum of these three terms is essentially f of average of f and k. Next, we combine the remaining second order terms. It's just a matter of standardizing the denominators. And we can then combine the respective v1 squared and v2 terms. We can make the substitutions. Let's also write k to the power beta in terms of the function f. Essentially, we replace k to the power beta by f, and the k to the power 2 times beta by f squared. It would make sense to replace the values at which the function and its derivatives are evaluated to the average of f and k as opposed to k. This shall give a better fit. So we replace f of k by f of average, and v1, which is the ratio of first derivative to the function value, by gamma 1, which is the same ratio, but both the numerator and denominator are evaluated at the average value. And same goes for v2. It becomes gamma 2. And let's make the replacements. Now we are on the home straight. We just need to deduce what form will this tau take for the Black model, which is the Black Scholes without the drift. Let's remind ourselves that we assume that the underlying follows the CEV process. Our function f was then power function, which we evaluate at the average of f and k. Gamma 1 and gamma 2 are defined as follows. The Black model assumes the following dynamics in our notation. So f of k is just the identity, and it will be evaluated at the average of f and k. Its first derivative is equal to 1, so gamma 1 is just 1 divided by the function value, and its second derivative is 0, so gamma 2 will equal 0. And if we represent the equivalent of tau asterisk for the Black model by tau underscore b, then it's easy to deduce that it will take this form. Just a matter of replacing the function in the gammas, and tau will be defined similarly as kinda total variance, but using the Black implied volatility instead of alpha. Let's substitute for tau in the two equations. Let's start with the CEV model. So we just substitute alpha squared times capital T minus T for tau, and we do the same for the Black model. Here we took the opportunity to simplify the terms as well. Now the price under the Black model will match the price under the CEV model if their taus are equal. So let's set them equal to each other. We just need to solve this equation for the sigma underscore b. It's a cubic equation, and you can try to determine its solution, which would be a complicated looking formula like an intimidating version of the quadratic, but such equations are usually solved in the approximate sense. We can get rid of the cubic term by noting that this term is small, and because alpha and sigma will be of similar magnitudes, we can replace sigma by alpha. This of course is an approximation. We can get rid of the residual maturity on both sides, and we can now easily isolate the Black volatility on one side by shifting everything to the right hand side. Now for small x, we know that 1 divided by 1 minus x is equal to 1 plus x, so this amounts to multiplying the numerator by the denominator, but with the signs of the terms after the 1 reversed. Let's do term by term multiplication, ignoring terms higher than second order and f minus k, and terms higher than first order and capital T minus t. Multiplying the terms in the first set of brackets by 1, we just get the first set of terms. Multiplying by the second term, we will only get one term because the other terms will be of higher order, so don't feature in our approximation. And same goes for the multiplication by the last term. We now combine the f minus k squared terms and the capital T minus t terms, and replacing the fraction by its expansion, we get the equivalent Black volatility. If you calculate this sigma, plug it into the Black formula, you will get the price which is approximately equal to the price that you will get from the CEV model. So this can enable one to use the Black model to generate a price that varies with strike or moneyness. Please give a thumbs up if you would like us to continue the series, and I look forward to seeing you in the next.